This video tutorial introduces the Gases and Atmosphere Chemistry unit. We will begin by looking at the properties of gases. However, in order to assist us, we need to do a quick review of the particle theory of matter. Now, this theory allows us to explain changes of state and many other observations in nature. In general, there are 5 major postulates to the particle theory of matter. The first is that all matter is made up of tiny particles. Notice how it doesn't make mention of anything about atoms or elements or compounds or molecules. We're just calling it a very generic term. We're just going to say particles for now. The second postulate states that all particles of one substance are identical. So, if I have substance A over here, these are A-type particles. Substance B, these are B-type particles. So different substance, different particles. The third postulate states that the spaces between particles are very large compared to the size of the particle itself, meaning that the distance between two particles is much larger than the actual size of the particle itself. Now, I know the drawing doesn't say it or show it very well, but it's not to scale. So, the related portion to this is that solids have the least amount of space between particles. So, for instance, if I have ice, it's very hard to put your hand through ice just because the spaces between the particles are very, very small. Liquids have more space between particles, so if you put your hand through water, you still feel some resistance, but it's much easier to put your hand through water than it is through ice. Finally, gases have the most amount of space between the particles, so it's very, very easy for you to slip your hand between steam, for instance. The fourth postulate states that the particles in matter attract each other. This is pretty important now. Particles in matter are held together by attractive forces. The closer together the particles are, the stronger the attractive forces. I like to think of this as magnets, where if you put a magnet very close together, you get a strong attraction force. On the other hand, if you have two magnets that are far away from each other, the force of attraction between them is very, very weak. So once again, the further apart the particles, the weaker the force. The closer, the stronger the force. Finally, the last point of the particle theory states that all particles of matter are constantly in motion. The more energy that the particles have, the faster they move. So for instance, I've got particles here that have high energy or are very hot. They're going to move very, very quickly. Particles that are very, very cold, or if the temperature is cold, they are going to move very slowly. So with that in mind, let's get started. Now, I apologize, this next section is pretty wordy, but it lays the groundwork for what we're going to be looking at later on. First, we define what is kinetic energy. Well, kinetic energy is the energy of movement, or the energy of motion. If you recall, solids have the least amount of kinetic energy, whereas liquids have a little bit of kinetic energy, and then finally gases have the most amount of kinetic energy. Here we see a diagram showing the gas state, liquid state, and solid state, and how the spaces between the particles are different. In the solid state, the solid particles are all locked into position, alright, because they're very close together. They have strong attraction for each other. Because of the strong attraction, these particles cannot move very much, so that's why they're limited just to vibrational energy. They can only vibrate and look in their spot. Liquids, on the other hand, have a little bit more room between them, right? More space. Because they have more space between them, there's less attraction. Less attraction means that they can still move around. Obviously, they can't just fly off anywhere they want, but they're still, relatively mobile, though limited in how they can move. Finally, gases have the most amount of space. Since they are very, very far apart from each other, the force of attraction between gas particles are very weak, which means that they are free to move around in any direction. This will be a quick clip to summarize what we've just learned.
Particles of a solid do not have enough energy to overcome the forces of attraction holding them together, and so cannot separate from each other. In a liquid, the particles have more energy and start moving more freely. In the gaseous state, the particles have the most energy of all the states of matter, allowing them to overcome the forces of attraction and move freely in space.
Both liquid particles and gas particles are in constant motion. However, the speed and average free path of gas particles are far greater than those of particles in a liquid. This is chiefly due to the far stronger forces of attraction between liquid particles in comparison with gas particles.
And so we use the particle theory to help explain why For instance, ionic compounds tend to be solid at room temperature, while polar molecules tend to be liquid, and then nonpolar molecules tend to be gases at room temperature. It all relates back to the attractive forces between particles. So for instance, ionic compounds generally exist as solids at room temperature because of the strong attraction between the oppositely charged ends. Now we know that sodium is a positive charge because it loses electrons to become stable. Chlorine is a negative charge because it gains electrons to become stable. We also know that sodium chloride is an ionic compound because its delta En is between, or rather greater than, 1.7. If you'll recall, we get the electronegativity numbers from the periodic table. So over here, sodium has an En value of 0.9, whereas chlorine has an En value of 3.0. And if we subtract the electronegative values, we get a 2.1. And since 2.1 is greater than 1.7, it is considered to be an ionic compound. So with an ionic compound, we show that they have a total positive charge, total negative charge, and over here, you notice that opposites attract. So total positive charge, total negative charge, they will have a strong attraction for each other. And as we saw before, a strong attraction from each other means that you're going to have a high melting point, because you need a lot of energy in order to break these things apart. And that's why sodium chloride, also known as table salt, has a high melting point of 800 degrees Celsius. You need 800 degrees Celsius of energy in order to separate the two compounds of sodium and chlorine. On the other hand, polar covalent molecules generally exist as solids or liquids. This is due to their moderate attraction for each other between the oppositely charged ends. Now, if you recall, polar covalent molecules are those that have a delta En value between 0.5 and 1.7. So if we check the periodic table, you'd find that hydrogen has an En value of 2.1, whereas oxygen has an En value of 3.5, which provides us with an En value of 1.4 if you subtract them. And since 1.4 is between these two numbers, it is a polar covalent molecule. Because of this moderate delta En value, we must show that there is a slight negative charge and a slight positive charge. And that's how we symbolize partial, with a delta sign. So instead of having a total positive, total negative, because of this high delta En, since we have a moderate delta En, we only get a partial negative, partial positive. And because it's a partial positive, partial negative, between these two water molecules, you get a slight attraction between them. All right, nothing as strong as this one over here, causing you to have a high melting point in order to rip them apart. Instead, you get a partial attraction, meaning the melting point for water is 0 degrees Celsius. Not as high as 800, but not very low either. It's just 0 degrees Celsius. Now, on the other end of the spectrum, we have covalent molecules. Covalent molecules generally exist in a liquid or gas phase. This is due to their very weak attraction between each other. If you recall, covalent molecules are those that have a delta En value of less than 0.5. In this case, chlorine has a 3.0, and this is another chlorine, so 3.0. If we subtract it, we get a delta En value of 0, and 0 is definitely less than 0.5, so we are a covalent molecule over here. Because it's a covalent molecule, no chlorine gets the electron more than the other, and so we have no overall charge on either of these atoms. Since there's no charge on either of these atoms, the attraction between them is pretty weak. It's the weakest of the three. As such, the melting point to rip apart these two molecules of chlorine is only negative 100 degrees Celsius. So negative 100 degrees Celsius is more than enough energy to rip apart these two chlorine molecules away from each other, just because they have a weak attraction for each other. Alright, so our next little segment is going to discuss the kinetic molecular theory of gases, also known as KMT. This theory explains the behavior of an ideal gas, which is an imaginary gas that helps us to model and predict how real gases would behave under regular temperatures and pressures. And we're allowed to do this because repeated experiments have shown that it doesn't matter what type of gas it is, as long as we're at regular temperatures and pressures, they all pretty much behave ideally. They behave as if it was an ideal gas. They behave identically. So instead of having to look at it on a case-by-case basis, we all just lump them into a one-size-fits-all model, and it does a pretty good job of predicting how gases will behave. When studying an ideal gas, you must understand that we are making the following assumptions. These assumptions are used to help us simplify our calculations, and we can do that because, well, it's close enough. So the first assumption we make is that since the volume of gas molecules is infinitely smaller than that of the system it is in, we consider the gas to have negligible or no volume. So what I mean is, if this is a water molecule, and if we had steam, well, a water molecule itself is very, very small. It's just a little pinprick over there. And the next closest water molecule to it would be way, way, way over here, right? Now, if I had a balloon, and it was filled with steam, the water molecule itself would be so very, 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 very small compared with the size of the balloon that really, if I added all the volumes, all this shaded volume of the water molecule itself and compared it to the size of the balloon, it wouldn't even be, it would be less than 0.00000000001% of the total volume of the balloon. And so it really wouldn't make any difference or make much sense to have to include or factor that into my calculations. So if the volume of the molecule itself, how much space it takes up inside the balloon, is so very, very small compared to the size of the balloon itself, it won't really affect our calculations, which is why we just say, well, you know what, let's pretend the volume of the molecule is 0. Make our calculations easier. We don't have to factor it in. And so we say the molecules themselves have no volume. The next assumption we make is that there are no attractive or repulsive forces between gas molecules. We're allowed to say this or assume this because gas molecules are very, very far away from each other. They have huge amounts of space between them. Because of this huge space between them, they have a very, very, very weak attraction for each other. So they pretty much don't affect each other's flight paths or movements. So it's easier for us to just say there are no interactions between gas molecules. The next assumption we make is that gases have high kinetic energy and move in random but straight lines. We also assume that when gas molecules collide with each other or the system walls, the collision is perfectly elastic, meaning that since gas molecules have so much energy, and if they bounce against the wall, the amount of energy they lose from bouncing against that wall is so very, very, very small compared with the amount of energy they actually have. And so because the amount of energy lost is so very, very small, we just pretend it's a perfectly elastic collision, meaning that no energy is lost in the collision itself. Finally, the last assumption we make is that the gas molecules have an average kinetic energy that's directly proportional to the temperature. So the higher the temperature, the higher their kinetic energy, energy of motion. The lower the temperature, the less kinetic energy they will have. Alright, so that pretty much covers the basic theory behind kinetic molecular theory, as well as the behavior of gases. In the next video clip, we'll talk about the practical applications, as well as the new formulas and equations and types of questions you'll be encountering in this unit.